Welcome to The Explainer. We're going to get into something today that's really at the heart of computer science, how we figure out how fast an algorithm actually is. It's the reason some of your apps are lightning fast and others, well, not so much. And it all boils down to understanding how functions grow. So let's just jump right in with a question that's a bit of a brain teaser. Which one do you think is bigger? N raised to the power of 100 or 2 raised to the power of n? I mean, at first glance, that n to the 100 looks like an absolute beast, doesn't it? But which one really truly grows faster in the long run? And here's the twist. The answer is, well, it depends on when you ask the question. See, it's not really about which one is bigger at a single moment in time. It's about their behavior over the long haul. As you're about to see, the one who wins the sprint isn't always the one who's going to win the marathon. To really wrap our heads around this, let's picture it as a race. We're going to line up 4 competitors, and each one represents a whole class of function growth. All right, so here are our racers. First up, we've got log n. This one's the slow and steady type. Then we have just plain old n. Next is n squared, which is starting to pick up the pace. And finally, our exponential juggernaut, 2 to the power of n. These are the kinds of growth rates you'll see all over the place, so getting to know them is super important. So let's look at the scoreboard right at the beginning of the race. For these really small values of n, things are, well, they're kind of messy. Log n is definitely taking its time, no surprise there, but check out n squared and 2 to the n. You're seeing that right, they're tied. When n is 2, they're both 4. When n is 4, they're both 16. Now, if you stopped the race right here, you might think, hey, maybe they grow at about the same speed. But that would be a huge mistake. And here's why. When we analyze algorithms, we're not really interested in the first few steps of the race. We care about the long run. We care about what happens when n gets massive, because that is where you see the true colors of each function. This quote from our source material really just nails it. Even for something that seems as ridiculously huge as n to the 100, there's going to be a point, a tipping point, where that exponential function, 2 to the n, not only catches up, but completely leaves it in the dust forever. This whole idea of focusing on the long term has a name. It's called asymptotic behavior. It's the core concept we use to compare functions. All it really means is that we pretty much ignore the confusing, messy results at the start and focus only on where things are headed as n gets infinitely large. So this is really the key difference, right? You've got the short sprint where things can be totally misleading. Functions can look like they're tied, they can swap places, it's chaotic. But then you have the marathon. As n gets huge, the real truth comes out, and a clear, permanent ranking just locks into place. And that moment, the instant that permanent ranking locks in for good, that's the tipping point. It's that specific value of n where the faster growing function grabs the lead and just never, ever gives it back. All right, so let's see how this all comes together in a final, undisputed ranking. Once we're focused on that long-term marathon, a really clear hierarchy of growth just appears. And here it is, the growth rate ladder. This lays it all out. At the very bottom, you have the slowest of the slow, the logarithmic functions. Take a step up, you get to linear growth, like n. Above that, you've got this whole category of polynomials, everything from n squared all the way up to our old friend n to the 100. But sitting at the very top, the undisputed champion, are the exponential functions, like 2 to the n. And I really can't stress this enough. Getting this order, this growth rate ladder, burned into your brain is one of the most critical things you can do in computer science. It's literally the foundation for how we figure out if an algorithm is any good or not. So we've had this abstract race between functions. But who cares, right? Why does this matter? Well, it turns out this has huge real-world consequences for the software we use every single day. This is where it all connects. An algorithm's efficiency is just its spot on that ladder. And here's the slightly counterintuitive part. A slower growing function, one that's lower on the ladder like log n, actually means a faster algorithm. An exponential algorithm, on the other hand, grows so ridiculously fast that as your input size gets bigger, it can become literally impossible to run. Picking the right algorithm can be the difference between getting an answer in a split second and waiting longer than the age of the universe. So I'm going to leave you with this final thought. Imagine you're building a search engine for a database with 1 billion items. Now that you know this hierarchy, are you going to pick an algorithm that runs in the linear time or one that runs in logarithmic time? The answer isn't just some academic exercise. It is the difference between building a system that actually works and one that fails spectacularly.